Hello, everyone. My name is Ana Petrović. I'm an assistant professor at the Department of Strength of Structures at Faculty of Mechanical Engineering, University of Belgrade. And my colleagues and I were dealing with the importance of welded joint characterization in construction designing. Okay, thank you. When every one of us dealing with structural strength models structure, preparing numerical method, finite element method analysis, we all model a structure using structural elements that affect rigidity without welded joints. But welded joints affect structural rigidity, especially in plastic domain. So the main idea of this paper is to prove that in elastic domain is allowed to ignore welded joints, whether in elastic plastic response, welded joints should be included into calculation also. And this analysis is based on inverse iterative methodology that was presented in some previous papers. And practically, the exit of that methodology is a new improved numerical model that is adapted and that includes all material properties of all three welded joint regions. That means that here you can see one typical, it's not working. Yes?
That's laser.
Laser?
Moraš rukom da pokažeš, ne radi na tome ekranu.
Okay, sorry. This is base material, this is weld metal, and this is heat affected zone. And heat affected zone is practically a mystery. So we developed a methodology to obtain characteristics of heat affected zone and to include heat affected zone into new developed numerical finite element model. So I won't be talking about this methodology, but the idea of this methodology was to improve numerical model using deformations obtained in the experiment by digital image correlation system. So the improved model is developed, and now we are going to apply these conclusions to two significant structures. The first one is a pipeline, practically a pipeline loaded with internal pressure that has stress state dominantly from membrane stress, and the girder of a bucket wheel excavator that is exposed to a bending force. So bending stresses and shear stress are present in that case. And we made three models of every structure. The first one was without welded joints. The second one contained welded joints, but heat affected zone had properties the same as base material. And the third one contained welded joints, and every zone of a welded joint had its own properties, including heat affected zone. Its properties were obtained using this inverse iterative methodology. So we developed those models. This is a pipeline, typical pump pipeline, loaded with internal pressure, membrane stress present. And those are results from that methodology previously developed. So here you can see pipeline, base material, you can see weld metal, and you can see heat affected zone. So we performed the analysis, and in all three cases, when internal pressure when deformation was in elastic domain, the results were the same. And explanation is simple. You can see this line that represents modulus of elasticity of all three materials, and they are practically the same. So all three models are the same. In that way, we confirmed that when you are in elastic domain, you can model a structure without welded joints. But much more interesting is what is happening when you are in a plastic domain. So the second model and the third model were developed. This is the first one. Those are the results. You can see a pressure that causes plastic deformation. And this is a model that includes welded joints. As you can see, this line is weld metal, and it has the highest strength. So stresses are highest in that zone as expected. And it is interesting to see here that stress concentration factor, when you include heat affected zone, real properties, stress concentration factor is lesser than when heat affected zone has the same properties as the base material. So this was the first analysis. The second one included this girder. It is practically a high profile. You have a force, vertical, and those lines are clamped as in a part of a real structure. And here are the results of force that still causes stresses that are in elastic domain. And also all three models are the same. But when you apply the force that is higher and that causes plastic deformation, the situation is completely different. So this is a model without welded joints, and you can see stress concentration factor estimated regarding this zone and regarding this one. Once again, the second model has welded joints are included, but heat affected zone has characteristics the same as the base material. And the third one, all three zones have their own properties. So those would be their stress concentration factors, but considering stress concentration factor when you have situation without welded joints, you can see that stress concentration factor when you have shear stress and bending stress is 1.64, and when you have membrane stresses, it's 1.5, I think. So this could be incorporated into standard and into when you design and project one structure, these stress concentration factors could be used. So, but look at these two structures. Is stress concentration factor actually the number that compares those two structures? When you look carefully and you look closely, you can see that stress gradient is completely different in those two structures. So maximum stress is not the one that should be compared, not just maximum stress. And I think that a more thorough analysis of this structure should be done that would include all the significant zones of this structure, whether stress is high in those zones or whether stress is low in these zones. Let me explain you our estimation of a failure of a structure. You have a structure, for instance, that has low stress in all the zones and high stress in just one zone. And you have a structure that has high stress in all the zones. Are those two structures the same? Considering yield strength, if those maximum and those maximum are lower than the yield strength, though they are both labeled as not failed, but they are not the same. So we would like, we use the probability of failure method to describe a structure using just one number that would be probability of failure. That would include stress in all important zones. So this one with the stresses that are the same in all the zones, and this one that has low stresses and high in just one zone, that one has higher probability of failure. So the next step is to perform reliability analysis of this structure. And of course, all those results should be confirmed by experimental testing of the real structures with welded joints. Those are simple structures, and those experiments could be performed easily. And before I thank you for your attention, I would like to invite you to this conference that will be held in Belgrade in November. And Professor Sedmak is chair of this conference. And I also would like to ask you to visit this conference. It's more theoretical conference, and it will be held in August next year. And it will be organized also in Belgrade.